In Chapter 5, we are looking at the graphs of trig functions. We are going to look at what the graphs of sine x and y equals cosine x look like. We're going to look at what their major characteristics are. We're going to look at what happens to those characteristics and the graph when they are transformed. Then we are going to look at some trig function application questions and how we can use the graphs to solve. And then we are going to look at a third trig function, which is the tangent function. Let's start with 5.1. And in 5.1 and 5.2, we are going to look at two things: what the graphs of sine and cosine look like, and how can we transform them. Y equals sine x and y equals cosine x are very different functions than the other kinds of functions that we've looked at in the course. They are what we call periodic functions. We're going to fill in this blank here. Periodic functions are functions that repeat the same function value, so the same y values, for a consistent change in the domain or x values. So what that means is sine and cosine have a very particular pattern that they follow, and the horizontal distance between that pattern is the same every single time. That horizontal distance between the start and finish of one cycle of the function is called the period. So because that horizontal distance is there and we have a period, it is called a periodic function. Trig functions are also sometimes called circular functions because they are based on the unit circle. So we are going to use some of our values from the unit circle to help us generate our y values on this graph. Then we're going to plot those points and see what kind of function we get. I'm also going to note in here that sine and cosine are often called wave function as well, wave functions, because the shape of the graph looks like multiple waves going up, going down, going up, going down, and so it takes on what looks like a wave, and so they're sometimes called wave functions. Let's start by looking at the basic graph of sine. So we have here a table of values, and we are going to look at the first two rows of this table of values. When we are graphing y equals sine x or sine theta, our horizontal values are coming from our angles. The y values are coming from the value of sine at those angles. So x is our angles, whereas y is our ratios at that angle. Where are we getting the ratios from? They are coming from the unit circle. So we're going to kind of look at the unit circle, and we're going to look at this table of values, and we're going to graph a sine function as we go. So we're going to start at an angle of 0, and hopefully remember from chapter 4 that at 0, we have a coordinate point here. When we talk about sine, we're only interested in the y value. The y value of the coordinate point here is 0. So sine of 0 is 0. At pi over 6, which is the same as 30 degrees, we have an x value of root 3 over 2. Our y value is 1 over 2, so the sine of pi over 6 is 1 over 2. At pi over 3, we're at root 3 over 2. And at pi over 2, our y value is 1. As we continue into quadrant 2, our next angle is 2 pi over 3. And at 2 pi over 3, you'll notice that because we're looking at the y value, it's still positive. And that y value is root 3 over 2. Then we're going to look at pi over 6, and the y value is back at 1/2. And then we get here, and we back at a y value of 0. So there's a definite pattern there. 0, 1 over 2, root 3 over 2, 1, root 3 over 2, 1 over 2, 0. So it kind of builds up and then builds back down. As we continue around the unit circle, notice that the numbers repeat that same pattern again. 1/2, root 3 over 2, -1, root 3 over 2, 1/2 is 0. So the numbers repeat again, but now in this second part of the table, we are in quadrants 3 and 4, and sign is negative there. So at 7 pi over 6, the y value is -1/2. And then y is equal to negative root 3 over 2. At 3 pi over 2, we're at -1. And then we go back, negative 3 pi over 2 and -1 over 2. So have a look at that pattern. If we take these points and now graph them down onto our coordinate plane right here. Here's 0, 0. At pi over 6, we're at 1 over 2. At pi over 3, at root 3 over 2. At pi over 2, we're at 1. And then we go back down. Root 3 over 2. Oops. 1 over 2. And then 0. -1 over 2. Negative root 3 over 2. -1. Root 3 over 2. -1/2 and 0. And if we connect the dots, there is one cycle of sine. How do I know that's one cycle? We went once around the unit circle. If we went again around the unit circle, it would just create that same pattern again. So this right here represents one cycle, this in blue, of sine. So let's talk about the characteristics of that graph. The domain, first of all, is going to be the set of all theta, such that theta is an element of the reals. There's no asymptotes here. There's no points of discontinuity. We have no jumps or anything. Theta is an angle. It can be anything it wants. It can be positive, negative, rational, irrational. It has no limits. The range here, though, we can see definitely has limits. Our x and y values, because we are on the unit circle, our x and y values were always between 1 and -1. So we can see here that when we're looking at just the y values from the unit circle, when we're looking at the sine values, again, 1 and -1 are our max and min. So our range for sine is the set of all y, such that y is greater than or equal to 1, -1, less than or equal to +1. If we have a look at what the x-intercepts are, again, because it's a periodic function and it's going to continue this same pattern forever and ever and ever, we have a bit of a problem with the x-intercepts. Even just on this bit that we've graphed here, there are 5 x-intercepts. And should we continue this graph, the x-intercepts are just going to keep emerging. So what we're going to do for the x-intercepts, because we can't possibly list them all, what we're going to do is we're going to state the x-intercepts using a general statement. Here's what I notice about where the x-intercepts are here. They're at -2 pi, at -pi, at 0, at pi, at 2 pi. So it seems to be at every pi we get an x-intercept, which makes sense because sine is equal to 0 when we're on the horizontal. When our terminal arm hits a horizontal on the unit circle, our y value is 0. So the way that we're going to write that is we're going to write it as pi n, where n is an element of the integers. So n can be 1 or 2 or 3 or 4 or -1, -2, anything we want. As long as it lands on the pi, that's going to be an x-intercept for sine. The y-intercept we can see right here is at 0, 0. And we want to show what the period is here. So we're going to show it here. It starts at 0 and goes to 2 pi. So this represents one cycle of sine, so one period. And for right now, that period is 2 pi radians, or if we were measuring in degrees, 360 degrees. Okay. What we also want to understand is that for the basic graph of sine, it follows this same pattern. sine always has a definite starting point at the midline, and then it travels up to the maximum. So this is the pattern that sine changes or takes on. It always starts at the midline. So the midline is halfway between the max and the min. Then it travels up to the maximum point. It turns and goes down and passes through the midline. It continues traveling down, down, down till it hits the minimum, and then travels back up and finishes at the midline. So no matter what we do to transform a sine function, it always does that same pattern. It starts at the midline, travels up to the maximum, back down through the midline, down to the minimum, and back again. So it's important that we recognize that this also represents one cycle of sine. Y equals sine x. That's what it's going to do. Let's have a look at cosine. So we're going to do the same thing. We're going to look at this table of values, but instead of looking at the first two, we're going to look at, still, x is our angle. Y now is our ratio, but it's our ratio using cosine. So when we think about the unit circle, we should remember from chapter 4 that when we're looking at the unit circle, cosine theta is represented by the x coordinates of our points on the unit circle. Okay, so when we have a look here, again, we start at 0. So there's our point on the unit circle. Our x value for that point is 1. So the cosine of 0 is 1. Then we are at pi over 6. The x value at pi over 6 is root 3 over 2. So the cosine of pi over 6 is root 3 over 2. We get to pi over 3, and our x value here is 1/2. And then we continue. We get to here, and again, our coordinate here, y would be 1. The x value there is 0. So our x values are getting closer to 0. Now, in quadrant 2, cosine is negative. So x equals negative 1/2. When we're at 5 pi over 6, x is equal to negative root 3 over 2. And when we get to pi, our x value is negative 1. So the numbers follow a pattern. 1, root 3 over 2, 1 over 2, 0, 1 over 2, root 3 over 2, 1. But because we are in quadrant 2 for this part of the table of values, our y values are negative. Continuing on into quadrant 3, at 7 pi over 6, we're at negative root 3 over 2. At 4 pi over 3, we're at negative 1/2. And because we are on the vertical axis, our x value would be 0. Now we're at 5 pi over 3 and positive 1 over 2. Cosine is positive in quadrant 4 because the x values are positive there. And then we'll be at root 3 over 2 and then back at 1 again. So you might notice that these numbers are the same numbers that are up in sine, but they just follow a different order. So we go from 1 to root 3 over 2, 1 over 2, 0, 1 over 2, root 3 over 2, 1. Root 3 over 2, 1 over 2, 0, 1 over 2, root 3 over 2, 1. It's the same pattern as we have up here, but in a different order. When we go through the quadrants for sine, we have positive, positive, negative, negative. When we go through the quadrants for cosine, we've got positive, negative, negative, positive. But they are going through those same values. So when we look at the graph of cosine, if we were to plot those points, so at 0, we are at positive 1, and then we are at root 3 over 2, and then 1 over 2, and then 0, negative 1 over 2, negative root 3 over 2, negative 1, negative root 3 over 2, negative, and we keep going. And when we plot those points and join them together, there is 1 cycle of cosine. So it does look different than sine. Okay, we can see that it does look different. These graphs look different, but they're passing through the same points, so they are going to have the same characteristics. So the domain is going to be the same for sine as it is for cosine. Same thing. X is an element of the reals, or theta is an element of the reals. The range, still between 1 and -1. The points for cosine are still coming from the unit circle. The unit circle only has a radius of 1. So it's always our x and y values are between 1 and -1. So range would also be the same as sine. X-intercepts is something that's going to be different. And we can see right away that on this graph right here, we can see we can see a couple x-intercepts. You can see 3 of them. I see one right at -3 pi over 2. I see one at -pi over 2, and I see one at 3 pi over 2. Oh, and pi over 2. So I can see 4 of them, but I know more are going to emerge. So as this graph keeps going, it's going to keep crossing the x-axis. So just like with sine, we're going to write the x-intercepts as a general statement. Now it seems to happen at the pi over 2's, -3 pi over 2, -pi over 2, pi over 2, 3 pi over 2. Here's how we write that as a general statement. It's for sure going to contain pi over 2, but we're going to write it as pi over 2 plus pi n, where n is an element of the integers. So what that means is we start at having an x-intercept at pi over 2, and then pi radians later, we have another x-intercept. Pi radians after that, we'll have another x-intercept. Pi radians backwards, we have an x-intercept. So there's pi radians in between each of our x-intercepts, and that's what that represents there. The y-intercept is also different. So we can see that because cosine has a bit of a different pattern than sine, that its y-intercept is also different. And we can see right here that the y-intercept is up there at 1. So that's another difference between sine and cosine. Sine has its y-intercept at 0 because it starts at its midline. Maximum, or cosine starts at its maximum, so its y-intercept is at 1. The other thing that you'll notice is that, especially when we graph sine and cosine on the same coordinate plane, we can also see an interesting difference between them. So let's go ahead and on the calculator, we're going to graph our two functions, y equals sine x and y equals cosine x. So we'll just get the calculator up here and graph those two. And we graph them just like we would any other function. So we go into y equals sine x. So a couple of things before we can go ahead and jump in and graph that. Let's put y equals cosine x into y2. So let's go ahead and just check the mode. So we're in radian mode. That means I'm also going to set my window in radians. I'm going to follow what we have right here in the notes. So our x minimum is at -2 pi. Now you'll notice you'll put it into your window. As soon as you hit enter, it changes it to the decimal approximate of 2 pi, and that's just fine. +2 pi for our x maximum. And for our y max and y min, for right now, I'm just going to put from -1 to +1 because that's our range. Now here's sine, and then following right after is cosine. So they have the exact same shape, very much the same, but you'll notice that it's like one is shifted over from the other. So if I could just take this graph right here and shift it this direction, or if I could take this graph and shift it this direction, they would be exactly the same. So what we're going to say is that sine and cosine, they differ by a shift of pi over 2 radians or 90 degrees. And we could shift it either way. So if we look at the cosine function, if I could shift it to the right pi over 2 or 90 degrees, it would become sine. And if I could shift sine to the left 90 degrees or pi over 2, then it would become cosine. Let's also just notice that cosine does start at its maximum. So if I was to list, kind of like we did up here, what a basic cosine function does, cosine will always start at its maximum y value and then travel down to the midline, halfway between the max and min. It continues traveling down until it hits the minimum point. Then it starts to bounce back up. It passes back through the midline and finishes up at the maximum. So no matter what we do to transform a cosine function, it will still follow that pattern. That right there is one cycle of cosine. And if we wanted to show that here as well, this right here is what it looks like graphically. This is one cycle or one period. So its period is the same. It's still 2 pi radians because it took us once around the unit circle to get one cycle of cosine. Now, when we talk about trig functions, we have to learn some new vocabulary that goes along with it. So we're about to learn 2 new words right now. For both the graphs of sine theta and cosine theta, we have the following attributes. The first attribute is amplitude. Now, amplitude is the vertical distance of the graph from the median or the midline, so from the median to either the maximum or minimum values. So amplitude has to do with the height of the wave. Now we need to be careful. Amplitude is not the total height of the wave. It is the height from the midline up to the maximum or from the midline down to the minimum. So it is half the total distance between the minimum and the maximum. We can find amplitude a couple of ways. We have an actual formula that's right here where we just take the maximum and minus the minimum, so find the total height and then divide it by 2. We can also find the amplitude by determining where the maximum is and then just counting down to getting to the midline. Whatever that distance is from the maximum to the midline, that's the amplitude. We could also take a given graph, find the minimum on the graph, and count up to the midline. That's also the amplitude. So we have a couple of different ways. This formula is not on your formula sheet. You need to know it. We should just state off to the side here that for the basic graphs of sine and cosine, the amplitude is 1. So amplitude is equal to 1 for our basic sine and cosine graphs. And that's because there is 1 unit between the midline and the maximum, 1 unit between the midline and the minimum. We should also note that amplitude cannot be negative because it is measuring a height. We should note that amplitude cannot be negative. A second piece of vocabulary we need to learn, and we've actually already talked about it, and that is the period. The period is the horizontal length of one complete cycle or interval. Horizontal length of one complete cycle or interval. Now, we know for the basic sine and cosine that the period is 2 pi radians or 360 degrees once around the unit circle. But when we transform functions, that period might change. So to determine the period given a graph of a function, which is something you're going to have to do, what we are going to do is we are going to subtract the x value of the start of the graph from the x value at the end of the cycle, or what we simply write as x end minus x start. Now, how do we know where a cycle ends and starts? That goes back to what we talked about here in terms of knowing the pattern. So if I want to find a sine function, I'm going to find a point on the midline that travels up. I'm going to follow through one complete cycle. Where it ends, I use that x value. Subtract those two x values, there's the period. For cosine, it starts and ends at the maximum points. So I'm going to find a maximum. I'm going to follow it through to the next maximum, take those x values and subtract them. There's the period. Now, we are going to go ahead and we are going to take y equals sine theta and y equals cosine theta, and we are going to transform them in a similar way like we did in chapter 1. However, a little bit different. We still have 4 parameters. However, 2 of our parameters have changed. So you'll notice that in the transformed form of the equation, we have a sitting in front of the function, so y equals a sine. B is inside the function. But then where we used to have h and k, now we use c and d. They still mean the same thing. There's still going to be a horizontal and vertical translation. But for trigonometry, rather than using h and k, we're going to use c and d. Let's talk about what those parameters are going to do. We already have an idea of what they're going to do because we've talked about transformations with so many other functions. But what we're going to talk about is, well, how is it affecting it in terms of some of the trigonometry language that we've talked about, like amplitude and period. And we're going to talk about a couple of other things as well. So let's talk about A. We know A is our vertical stretch factor. And it continues to be our vertical stretch factor. So what that actually does then is it makes the wave either taller or it makes the wave shorter about the horizontal axis. So because it's stretching and making it taller and shorter, that has to do with the amplitude. So A is going to affect the amplitude. In fact, the amplitude is actually going to be equal to the absolute value of A. So whatever our vertical stretch factor is, that's the amplitude of the graph. That's going to tell us how far the distance is from the midline to the maximum or the midline to the minimum. Now, we know that A, if A is less than 0, that means we have a vertical reflection. And that happens here as well. So what happens when we have a vertical reflection is it's going to just change our patterning here. So when we vertically reflect a sine function, all of this stuff will move here and all of this stuff will move here. So what it does is it takes this and it reverses the order. So we still start at the midline when we reflect it vertically, but instead of moving up to the maximum, we move down to the minimum, then up to the midline, then up to the maximum, and back to the midline again. So vertical reflecting is just going to change the order of the pattern for sine. For cosine, what happens is all of this is going to move down here, all of this moves up here, this moves down here. So when we reflect it vertically, what ends up happening is it follows the pattern, but these switch out. So it goes from the minimum up to the maximum, back down to the minimum again. So that's what happens when A is negative and we have a vertical reflection. Again, we need to be careful. If A is negative, but we are commenting on the amplitude. We use the absolute value of A because we said over here that the amplitude cannot be negative. So that's why we're using the absolute value of A. Let's talk about B. B is our horizontal stretch factor. And we know from lots of doing transformations that when we are given a value of B, our horizontal stretch factor is the absolute value of 1 over B. So when we talk about a horizontal stretch, that means our graph is either going to get squished up horizontally or stretched out horizontally. We're talking about changing that horizontal interval. That interval is called the period. So the period is affected by B. In fact, we can calculate the period if we know B. The period is equal to 2 pi divided by B. And that's because originally the period is 2 pi radians. We're stretching it by a factor of 1 over B. 2 times 1 over B is 2 pi over B. I'm also going to state that if we have the period, so if we have the graph, that we can also calculate our B value. So we have this little formula that period is 2 pi over B. We also should recognize that B is equal to 2 pi over the period. So we can add that in there as well. Okay, let's go ahead and talk about C. In chapter 1, C would represent our horizontal translation. And it does here as well. However, we also can refer to it as the phase shift. So we use a bit of a different vocabulary with trigonometry. Horizontal translation, same thing as phase shift. Now what phase shift does is it actually tells us what the starting point is going to be. So it tells us the start point, the x value of the start point for the graph. So we talked about needing the start and the end point to determine the period. The C value tells you what that start point is. D is our vertical translation, so moving the graph up and down. However, we don't usually call it a vertical translation. In trigonometry, we call it the vertical displacement. And what it actually does is the vertical translation, whatever that D value is, because it's moving the whole graph up and down, the graph is still going to stay symmetrical about that midline. So the midline's at the x-axis. When I move the whole graph up, the midline becomes our D value. So the midline ends up being equal to D. We also have two other little formulas that we need to talk about. So knowing what the amplitude is, it's the difference between the midline and the maximum, or the midline and the minimum, and understanding that the midline comes from the vertical displacement, that gives us two little equations. The maximum y value then can be found by going from the midline D and adding the absolute value of A, adding the amplitude. The minimum y value can be found by taking the midline D and subtracting the amplitude, which is the absolute value of A. So if we know where the midline is and we know what the amplitude is, we can easily find our max and min. That becomes important because that is going to become our range. So we'll be able to find those characteristics based on those two little equations. I'm going to write the other one for period here. B is equal to 2 pi over the period. We're going to need that as well. So putting together what we know about chapter 1, putting right now what we've learned about what these two functions look like, let's go ahead and do some examples of analyzing these graphs. So here's the first one. we are given the function y equals 4 sine 1/2 theta plus pi over 3 plus 1. So let's identify our parameters here. We can see that the 4 is A. We can see that the B is 1/2. And now here's where some alarm bells need to go off a little bit. This pi over 3 is not going to be our C value. Hopefully we notice up here in the general form, just like with the other functions, that the B is factored away from our horizontal translation. So that has to be the same thing in this function here. That B value has not been factored out. So I need to be careful about what the C value is there. Our D value is 1. So let's rewrite this function with the correct B value factored out and then therefore the correct C value written. So this is going to be y equals 4 sine bracket, take out that factor of 1/2. Now we need to be careful. Pi over 3 divided by 1/2 is like pi over 3 times 2. It becomes 2 pi over 3 plus 1. Okay, so we said that A is 4 and A represents our amplitude. So for amplitude, we're going to put 4. Again, just pay attention. Even if that A value is negative, we are going to use the positive form of it. Amplitude is the absolute value of A. B is 1/2. So if we think about it, it's being stretched by a factor of 2. When we want to calculate the period, we're going to use that formula, 2 pi over B. So it's going to become 2 pi divided by 1/2, which is equal to 2 pi times 2 over 1. We're going to reciprocate that bottom fraction, which gives us 4 pi. If we were to do this in degrees, same process, 360 divided by 1/2 is equal to 360 times 2 over 1, which gives us 720 degrees. So it has been stretched by a factor of 2, or just use the 2 pi over B. Next, we can see our C value is 2 pi over 3. So for the horizontal phase shift, we're going to put in the 2 pi over 3, but we must give a direction because it's plus 2 pi over 3. It's 2 pi over 3 to the left. So for the horizontal phase shift, please don't just say 2 pi over 3 or positive 2 pi over 3 or negative 2 pi over 3. Give a direction. So you need to specifically state, is it to the left or is it to the right? And again, what we're looking at there is the C value. Finally, our D value is positive 1. That's our vertical displacement. And same thing with this one. Please give a direction. So don't say positive 1. Don't just write 1. Write 1 up. So give a direction. And in this case, that's either up or down. And that comes from the D value. Okay, domain. Domain is pretty easy to do for all of these. Domain is never going to change. It's always going to be x is an element of the reals or an integral notation from negative infinity to positive infinity. And domain, again, unchanged, never changes, always the same. Our range and our max and min go together. So for our maximum comes from D plus the absolute value of A. So in this case, that's going to be 1 plus 4, which is 5. Our minimum comes from D minus the absolute value of A. So that's going to be 1 minus 4, which is negative 3. You could also think about this in terms of transformations. So originally, sine is going to be between 1 and negative 1. When we stretch it by a factor of 4, now it's going to go between 4 and negative 4. And then we move everything 1 unit up. So it's going to go from negative 3 to positive 5. So for max and min, you could also get those values just by thinking about the transformations. Once we have them, we could go ahead and write our range now in interval notation from -3 to 5. So looking at the parameters, that's going to help you write all of the characteristics of the graph. Let's look at example 2. Example 2 says compare the characteristics of the graphs f at x, which is -3 sine 2 pi x minus 5 plus 5, and g at x, which is 2 sine 2x minus 5 plus 6. Very, very important that anytime you are given a compare question, that you don't just, first of all, don't just list the characteristics and leave it. When you compare, you must actually state what is the same. So state the similarities and the differences. So we are going to list out what some of these characteristics are for both f at x and g at x, but you can't just list the characteristics and leave it at that. You must list your characteristics and then state what is the same and what is different. So let's go ahead and let's look at f at x and let's talk about what some of its characteristics are. Here's what we're going to comment on. So for f at x, we're going to talk about the amplitude. We're going to talk about the period. We're going to talk about the phase shift. We are going to talk about the vertical displacement. We're going to talk about the maximum. We're going to talk about the minimum. So pretty much all of those same characteristics that we talked about in this previous example, we're going to talk about here. Amplitude. Let's be careful. Amplitude comes from your A value. Your A value here is -3. The absolute value of -3 is 3. Period comes from the B value. The B value is 2 pi. 2 pi over 2 pi, because remember that to find the period, it's 2 pi over B. The period here is 1. Our phase shift comes from C. Nice to see in this one that the B value has already been factored out. So when we have an x minus 5, that means it's moving 5 units to the right. The vertical displacement is our D value. It's a +5, so 5 units up. Our maximum comes from D plus the absolute value of A, so 5 plus the absolute value of -3, which gives us 8. Minimum comes from 5 minus the absolute value of -3, which is going to be 2. So 5 minus the absolute value of -3 will be 5 minus 3, which is 2. Okay, let's talk about g at x. We're going to look at those same characteristics. We're going to look at the amplitude. We are going to look at the period. We're going to look at the phase shift, the vertical displacement, the maximum, and the minimum. The amplitude for g at x comes from its A value, which is 2. We don't need to worry about absolute value there because it's not negative. Period is found by using the B value. 2 pi over B is going to be 2 pi over 2, so the period is pi. Phase shift, x minus 5, the B value's been taken out there, so 5 units to the right. And then from our D value here, it's been moving 6 units up. Our maximum comes from D plus the absolute value of A, so 6 plus 2, which is 8. The minimum comes from 6 minus 2, which is 4. But we can't leave it at that. So compare doesn't mean just list the characteristics. We have to state what is the same and what is the difference. So what is the same between f at x and g at x, and what is different? So I can see that the amplitudes are different. I can see that the period for each is different. I can see that both have the same phase shift. It's both moving 5 to the right. We can see that the vertical displacement is different. we can see that the maximum is the same for these graphs. They're both at 8, but their minimums are different. Good. So really, really important that this is a good way to do this question. List the characteristics of the other function, but at some place you have to state what the similarities and differences are. That's how we do a compare question. Example 3. The function y equals -5 sine theta plus pi over 3 plus d has a maximum of 8. What is the value of d? So in this case, we know our maximum value. We know kind of what our equation looks like, but we're missing that d value. So let's remember what the connection is between the maximum and the d value. Maximum is equal to d plus the absolute value of a. Well, we have the maximum. The maximum is 8. We don't know d. We have a. A in this case is -5, so the absolute value of -5 is +5. So 8 equals d plus 5, and just subtract 5 from both sides. D is equal to 3. So those little formulas, those maximum and minimum formulas, really help us when we are solving some of these questions. Okay, now a bigger challenge comes up when we are writing the equations based on a graph. So in all of these examples that we've done, the equation was provided for us, and what we were doing was listing the characteristics. Now what we need to do is we need to write equations for a given graph. So I do this stuff in a bit of a particular order. And what we have to recognize is that if I just gave you this graph, it's really hard to tell right off the bat if we want a sine function or a cosine function. And in fact, in this question, we're going to write both. We are going to write 2 equations that show a sine function and 2 equations that have a cosine function. Here's what's really nice is that when we are doing this, when we are taking a graph and writing it both as a sine or a cosine, is that some of these parameters are the same for both. So we are going to make a little note here that A, the amplitude, B, the value that helps us determine period, and D are going to be the same. So those are going to be the same for all the functions for this graph, for all functions written for this graph. After that, the only difference is going to be C. So whether we're doing sine or whether we're doing cosine, A, B, and D are going to be the same. It's the C value that's different. So let's start off with what some of those values are going to be. Let's start with the amplitude. So a couple of different ways that we can calculate the amplitude. We can use the formula that we wrote a little earlier in the notes, and that is to take the maximum, subtract the minimum, and divide by 2. So the maximum in this case is at +4. The minimum is at -2, so 4 minus a -2 divided by 2 is going to be 4 plus 2 divided by 2, which is 6 divided by 2, which is 3. So A, our amplitude in this case is 3. Our vertical displacement D, we actually have another little formula for D. Since D is in the midline, it's kind of like the average. So we can go maximum plus the minimum divided by 2, which is going to be 4 plus -2 divided by 2, which is going to be 2 over 2, which is 1. So our D value is 1. We can do those a different way, right? So we can go from the maximum to find D. We know that our amplitude is 1. So from the maximum, count down 3 units, 1, 2, 3, and we end up with a y value of 1. We can go from the minimum, count up 3, 1, 2, 3, and we end up at a y value of 1. So we do have a couple of formulas that are going to help us out. They're not on the formula sheet, and you don't have to use them, but they are helpful when we are doing this. Okay, so next what we need to do is we are going to find a C value. So we have to sort of decide where we want to start. For this example, I'm going to start with a sine function. So I'm going to look at sine theta, and specifically I'm going to look at sine theta whose amplitude is positive. So what that means is it starts at the midline and it starts to increase. It travels up to the maximum. So to help me out, I'm going to dot the midline in. So I know the D value is 1. So I know that that is where the midline is. And I'm going to just dot it in. So when the A value is positive for sine, it starts on the midline. So let's look first at all the possible midline spots. This is where the graph hits the midline. Now, because A is greater than 0, I don't want just where it hits the midline. I want it where it hits the midline and is traveling upwards. So this first point that I've got right here is not great because it's at the midline, but the graph is decreasing. So I'm not going to use that one. This is a good possible starting point. The graph has hit the midline and is increasing. This is not a good starting point. Keep going. This is a good starting point. This is not. And this is a good starting point for sine. Again, because that A value is positive, we want it starting at the midline and traveling up. So which one of those 3 am I going to use for the X start? We're going to use the one that's closest to the Y-axis, which is this one right here. So we're going to use the one in the middle. So I'm not going to use this one. I'm not going to use this one. And again, we're looking at the X coordinate. So looking down, that X coordinate right there is going to be right in between 0 and pi over 3, which is pi over 6. So our X start is going to be pi over 6. That is also our C value. Normally, cosine starts at the midline right on the y-axis. This one starts at the midline over here. It has been shifted over pi over 6 units. So our X start is our C value. Okay, let's follow through one complete cycle. Up to the maximum, down through the midline, down to the minimum, back to the midline. There is one complete cycle. So let's get our X end point there. So it starts at pi over 6. It goes all the way through. And notice right here, it stops between 2 pi over 3 and pi. So that's going to be here at 5 pi over 6. It ends at 5 pi over 6. That means we can figure out what the period is. The period is always going to be X end minus X start. That means that we're going to go pi over 6, 5 pi over 6 minus pi over 6, which is going to give us 4 pi over 6, which reduces to 2 pi over 3, which is great, but I need to know the B value. I have my A, I have my D, I have the C, I have the period, I need B. So B is equal to 2 pi over the period, so 2 pi over 2 pi over 3, which is 2 pi times 3 over 2 pi, which is 3. So our B value is 3. So B takes the most amount of work. You have to figure out what the period is and then 2 pi over the period to get the b value. So far, here is the equation we have. Y equals positive 3 sine positive 3 theta minus our start point was pi over 6, so that's our phase shift, plus 1. Now, we want to do this same thing. We're going to stick with sine, but we want the a value to be negative. So here's what I know. I know a, b, and d are going to be the same. So y equals, well, it's going to be a negative 3 sine, b is still going to be the same. Theta, something's going to go in here. The c is going to be different, plus 1. Now, all of those starting points that I erased before, those are now up for grabs. So because we're looking for where a is less than 0, we want where it's hitting the midline and decreasing. Here's a possible start point. Here's a possible start point. Here's a possible start point. Which one of those 3 are we going to choose? We're going to choose the one in the middle because it's closest to the y-axis. We want the smallest possible shift. So we'll notice here what the x value is. So when a is less than 0, it starts at negative pi over 6. So that's going to be plus pi over 6 as our c value there. Let's do cosine. We need to do 2 equations for cosine, but again, here's what's nice. Our amplitude is the same, so positive 3 cosine. B stays the same. C is going to change, so we'll just leave a space for C there, and then we're going to put a plus 1. So cosine always starts at its maximum. So here's our possible start points for cosine. There are 4 of them. We want to choose the one that's closest to the y-axis. So we actually have 2 possibilities because these are both equal distance. So the x values there are pi over 3 or minus pi over 3. We can pick either one. So we can put plus pi over 3 or minus pi over 3. Both of them are good starting points. Our fourth and final function, negative 3 cosine. B value is 3. We're going to figure out what C is, plus 1. When cosine has a vertical reflection, it starts at its minimum. So there's our potential starting points for a cosine function whose a value is negative, who's been vertically reflected. Which one are we going to pick? We're going to pick the one that's closest to the y-axis. We have one that's right on the y-axis. What does that mean? That means it has not been shifted. So we don't have a C value. So we can put plus 0 there or just leave it as 3 theta. So we could even just clean this one up a little bit and we can write it as y equals negative 3 cosine 3 theta plus 1. Now, we used sine to start. We could have easily started with the cosine. I do just want to show you that we could have found the period using cosine as well. So if we decided to start with that instead of looking at the sine function, we would still do the x end minus x start. So if I chose this maximum point to start at, let's just erase some of this stuff. Here's one complete cycle of cosine. We would still do x end minus x start, and it would be pi over 3, that's where it ends, minus negative pi over 3, which is pi over 3 plus pi over 3, which is 2 pi over 3, and then we would get that same b value. So it doesn't matter what you use to calculate the period. You can use the cosine function to calculate the period. You can use a sine function to calculate the period. It's going to be the same. It might be a bit easier to use a cosine because it's easier just to find the maximums. Sometimes it's tough to find where the midline is and traveling up for sine. But what we need to understand is that once we found A, B, and D, it's going to be the same for all the functions. The C value is going to change as we change from a positive A to a negative A, or from sine to cosine. Last example here, we have write an equation that represents a cosine function with a period of 270, an amplitude of 3, and the first maximum point is at 38. Okay, so it might be a good idea here to start off with our basic form. So y equals A cosine B theta minus C plus D. Now, a couple of these things we can recognize right away. We know that the amplitude is 3. So we know the A value is going to be 3. So y equals 3 cosine. We have the period, so we can calculate B. B is equal to 2 pi or 360 divided by the period. So 360 divided by 270, which is going to give us, and that just reduces to 4 over 3. So B is 4 over 3. Now, the C and the D, we're not quite sure about. All we know is the first maximum point is at 38. Well, cosine starts at the maximum. So since we have the first maximum point is at 38, this right here is our x start. We're looking for a cosine. Cosine starts at the maximum. This first maximum has an x value of 30. Our x start is always our c value. So because it's a positive 30, it's going to be x minus 30. Now, our maximum value is 8. So we can see that our maximum is 8. We also know our amplitude is 3. That means we can calculate D. We actually did this earlier. Maximum is equal to D plus the absolute value of A. We know the maximum is 8. We're trying to find D. A is 3. D is equal to 5. So plus 5 on the end. So amplitude we were given, that's A. We were given the period, so we can calculate B. We were given just one coordinate point on the graph, but because it was the first coordinate point, we recognize that that's our x start, so our C value, and then using one of our formulas, we can find the D value. So that is our transformations of trig functions. Next, we will be looking at trig applications.